Okay, so finally, the vector calculus paper, we are looking at it. But before we get into this, I want to quickly talk about two things. The linear models paper I said, I won't be like properly going through it, but I just want to say the reason why I won't be making a video on it is because it is just a bunch of calculations. Estimate the slope parameter, that's a calculation. Building an ANOVA table, that's just calculations. This is all just slapping something into a calculator and hoping you got it correct. There's a couple interpretation things here, but you need the numbers for those. So there's not a point, yeah. I'm just flashing up the pages now in case you want to pause and read. But yeah, I don't think this paper is interesting enough to warrant an entire video about this paper. So yeah, pause and read that if you'd like. Yeah. This last page here. Yeah, so that was out of 100 marks. That went okay. I kept being dumb and forgetting how many degrees of freedom I need for certain tests. But the second thing I wanted to talk about is just the cheat sheet I brought into the vector calculus exam. If I can get it open, there you go. So what do we have on here? We have some properties of conservative vector fields. We have this painful result here that I really should know off by heart, but you can never be too careful. That the curl of the grad is 0. What else? Now that's actually wrong. Oh my word. Okay, yeah. So I'm saying that for the vector x, y, z, the size is just x plus y plus z. That is incorrect. Oh my word, I'm an idiot. Yeah, thankfully I didn't use that in the exam. My word, that's embarrassing. The radius is our vector is perpendicular to curved walls. Just a trick my vector calculus lecturer told me about for some of his exam questions that I think appears in here. In this paper, that is. Solenoidal, yeah, divergence theorem, Stokes theorem, Green's theorem, some identities that I didn't really use. Jacobian matrix, a Stokes theorem example. On the other side is I believe another Stokes theorem example. A surface integral, actually. Never mind. Directional derivative, which is actually one of the easier things to do on this course, but I never actually practiced it, so I had to put an example on there. Work done formula, but that's literally just a line integral. I didn't need to put that on there, and that's an example there. This is an example question from the 2023 paper, the solution to it, in hopes that I'd give me some ideas in case a question similar to it came up on this paper. I can't remember if it did. Let's see. I sat this paper on the... I couldn't tell you. I'm going to say maybe 2nd of May. I don't know. I really don't know. Oh, wait, no. It was last Tuesday. It was last week Tuesday, yeah. The 7th of May. But let's get into this. Yes. Okay, question 1. Find the directional derivative of phi. Where phi is that? Yeah, directional derivatives were quite often the first question of these papers, so I just thought I may as well put an example on there and just copy that out once I get to it. I'm going to find the angle between these surfaces. Yeah, this just involved taking the normal of these surfaces, then getting the angle of these using the dot product formula. Here, compute an appropriately chosen derivative to show that f is a conservative vector field. Of course, that is just getting the curl of it. So that is grad cross f. Find the scalar potential for f. I believe, from what I remember, that just involves integrating this part with respect to x, integrate that with respect to y, and that with respect to z. And then I guess the union of those functions is your scalar potential. Yeah, not too bad so far. Hence, to evaluate that line integral where c is the path given parametrically by x of t, y of t, and z of t, in which t is between 0.5. Yeah, this question wasn't too bad. You just gotta get the start and end points of each of them. Because it's conservative, the line integral is just dependent on the start and end points. Not too bad, not too bad. Ooh, this line integral question, I think I might have messed it up because I got an answer that I think one of my friends didn't get. I only compared answers with this question with one other person. I'll just read it first. Let C be the triangle traced anticlockwise in the xy plane with vertices 0, 0, 3, 0, and 0, 2. Evaluate that line integral in which S measures arc length. Now, I believe for this I got -18, but someone I spoke to got like 33 or something. So yeah, who knows? I vaguely remember doing a question like this in like a past paper I attempted, but because it didn't seem too hard to me, I thought, you know what, I ain't got to practice that again. I'll leave it and focus on the harder stuff. And I ended up forgetting, so, you know, that's what I get for having confidence in my maths ability. Next part, find the length of the curve C defined by R equals 3 cosh of 5t plus 2. Now, this term here, I've heard the pronunciation shine, I've heard the pronunciation cinch, I've heard shin, I've heard everything. I used to say shine, but then my lecturers started saying cinch, so now I just say cinch, 2 cinch of 5t plus 15t. Give your answer in the form. Now, I couldn't tell you the last time one of these papers had a hyperbolic function in it as the R vector. It is normally just regular trigonometry, which actually kind of caught me off guard. But thankfully they have these identities here, which made it possible in the end. Was a little bit of manipulating this, but yeah, I remember I had to, what did I even do? I think at one point I had to bring this sinh squared to the other side and then sub in to whatever the hell I got. But yeah, because first you need dr by dt and then the length of that vector dr by dt. Then you manipulate these pretty much. Yep, first 3 questions weren't too bad, except for that part where I got a little bit stuck. But hey, other than that, could have been worse. Question 4. Let R be the region in the positive quadrant bounded by the curves 4x squared minus y squared equals 1 and equals 3, and the straight lines 2x plus y equals 3 and 2x plus y equals 5. Find the area of R, giving the answer exactly, but not as a decimal approximation. I cannot read. It's currently about 1:20 in the morning, so a little bit tired. I'll be going to bed soon. But yeah, this wasn't too bad either. Just using the Jacobian matrix that I put on my cheat sheet that I've thrown into my bed now. It'd be a little bit awkward getting to it, but oh well. Yeah, Jacobian matrix for this one wasn't too bad. For this one, I believe what I did was you had to set this equation 2x plus y to some like, I don't know, like what's the term I'm looking for, to something like u. Let's say for example we said u equals 4x squared minus y squared, and then we said v equals to 2x plus y. You had to take those equations, rearrange them so you get that in terms of u and v, and then also slap the Jacobian matrix in that integral, and then use these as limits, because you get to your integral in terms of du dv instead of dx dy. So your limits become 1 and 3 and 3 and 5. So yeah, that was interesting. I believe in the end, if you rearrange it, I believe if you do have u as vx squared minus y squared and v as 2x plus y, I believe you get v squared minus u all over 2, I think. That sounds right from what I remember, yeah. Okay, so that is, oh, I should have said, this is the start of section B. Same as all exams, I have 100 marks. You do all of section A, and then section B, you answer 2 questions. There's 4 questions in section B. You answer your best 2 questions that you attempted will count towards your mark. Section A is 60 marks, section B is 40 marks. But yep, let's keep looking. Yay, this one. Let A be greater than 0. The straight line segment C1 starts at and ends at C2 is a curve, y squared equals 4ax traversed from The diagram below shows C1 and C2. By evaluating both sides of the equation below, verify that in which f of xy equals that and g of xy equals that. C is the closed curve comprised of C1, C2, and D is a finite region enclosed by C. Now, if I'm not mistaken, this is Green's theorem, and I attempted this question, not at first, but my attempt was to start off with the right-hand side, but that just didn't work out, so I gave up in the end. Yeah, I thought that because it was Green's theorem, it wouldn't be too bad, and there actually was a proof of Green's theorem in the notes that I decided not to put in my cheat sheet because I thought I wouldn't need it. Yeah, my laziness keeps coming back to bite me with these cheat sheets, I've noticed, and I just simply don't learn. Maybe someday, but yeah, I attempted to start with the right-hand side. It became ugly, so I gave up. Next question. Question 6. Well, I mean, this one's scaring me a little bit when I saw this shape. I find the divergence of that. Simply just grad dot f, not too bad. Write your answer in the form p r to the q, where r squared equals and p and q are natural numbers to be found. I believe what I got for this was 3r to the 4. It was definitely to the 4. It might have been a 3 or a 5 here, I can't remember. But yeah, that wasn't too bad. Those first 6 marks were fine. Let V be the volume in space bounded below by z equals r squared and bounded above by z equals 2 minus r squared, in which r squared equals that. Use the divergence theorem over there to evaluate the surface integral, where S is the boundary of V oriented with an outward normal. Now, things got a bit tricky here, because, so, of course, use the other version of the other side of the divergence theorem with the triple integral, and then you get the divergence of f in that triple integral, but we got that earlier to be, I think, 3r to the 4. Slap that in there, and then to be perfectly honest, I didn't know what to do past that point. Yeah, I attempted changing the limits and stuff by getting it in terms of like dr and everything, but yeah, no, I think the person marking it can tell that I panicked and didn't know what I was doing. But yeah, question 7. Oh, this question, man, I'm so sad about this one. Show that f cross, what am I talking about? Grad cross 5y squared minus 3z squared I equals that. Fine, simple curl calculation. Let S be the surface defined by z equals xy times 4 minus y minus 4x. For positive x and y, and y plus 4x is less than or equal to 4. Use Stokes' theorem to evaluate that. What's really annoying is I damn near skipped this line, reading this line. I just saw this and I thought, great, a surface integral, I'm good at those. That's going to be great. And as I was doing it, I reread the question and I saw Stokes' theorem, which means we have to use the line integral version of it. And I thought, that's not too bad either. I tried it, and when I put that into the integrand, I thought, okay, we don't know what z equals. Let's put that in there. Then I realized, hold on, I'm gonna have to square this. That can't be it. I tried it, but yeah, I ran out of time in the end. I'm pretty sure I got these 6 marks. Of these 14 marks, I don't think I'll get any for solving it as a surface integral and then backpedaling. So, well, fellas, I may have actually just gotten the 6 marks in this question. Unfortunate. But yeah, that was a bit rough. Overall, this paper, section A was just fine. I like section A a lot. It wasn't too hard, and the hyperbolic distance question was quite nice. Section B, question 4 wasn't too bad either. I got that done quickly, but yeah, past question 4, it was just a game of how quickly am I losing confidence in my ability to just count at this rate. But yeah, that is the vector calculus paper. Next video will be the physics paper that I sat technically yesterday now. I won't film that now, I'm quite tired. I'll film that, maybe not tomorrow. Tomorrow's going to be a grand session for algebra, that's on Thursday. So I'll probably film 2 videos on Thursday, one being physics and one being algebra. So see you then.